energy dissipation in different scale of data exchange. The basic problem is you can see this part of the communication that global on-chip movement of data is power hungry. That means when we have a chip, we want to transfer data from one end of the chip to another, the whole chip, that energy is never going to scale. That's why we need to pay attention. How do I reduce this level of data exchange? So that's why we, researchers for last decade or so have been working on different types of novel interconnect paradigm. Instead of planar metal wires, three-dimensional integration, chips are 3D, 3D chips are in the market. Then photonic interconnects and wireless or RF interconnects. These all different types of interconnects, their aim is to achieve high bandwidth and low energy dissipation. But these are enabling technology. How do I use an enabling technology to design a highly integrated system? So we have to go back to a little bit, past in the history. So a two-dimensional mesh, that's the easiest way to integrate multiple cores in a system. And this is the most well-known parallel architectures. But as soon as you talk about CPU and GPU together, your data exchange pattern becomes kind of complicated. So basically what will happen, there are many GPUs and few last level cache controllers. So basically all the GPUs, they are trying to access those LLCs. And what is happening, you are going to bottleneck a certain amount of links. Think about a traffic highway. You are trying to take, everybody is trying to take a particular route. And that route will, that path will be highly congested, no doubt about that. So first point I am trying to make here, that something like a mesh is going to fail. It's easy to design. As you can see, very regular architecture. You don't have to worry about where to place what. But this is never going to scale in this kind of heterogeneous architectures, CPU, GPUs together. So what next? If you take a look at natural complex networks like brain, microbe, social networks, they have this very interesting property of small world networks. And they are also resilient to attacks. We are in the in CySER security is one of the theme. So you need to understand when we are just consider the example I gave in the previous slide. Already in a mesh, some of the links are very, very highly utilized. Now you have a rough agent on the chip and they attack those links. Then that system is going to fail. So small world networks, they are very robust against attacks. Scale-free graphs are robust against random failures. So, and in all my slides, I have provided you guys with the reference. Actually, in a simple mesh, if you introduce few shortcuts, that gives rise to small world effect. And first time, this paper from Radu Marculescu, he was in CMU then, they showed that how we can design, how we can induce small world effect by inserting few long-range shortcuts in a mesh network. Because once again, I'd like you to understand that designing a mesh is easy. You really don't have to worry about complicated routing algorithm or anything else. So from these, so that work inspired us, and real small world networks, they follow this power law based connectivity. So what will happen we'll have many short range local links, and then few long range shortcuts. But we need to understand, when we are talking about long range, longer links, your normal metal wires are not going to scale. And there come the role of emerging interconnects. As I said, 3D or photonics or wireless, they are faster than your normal metal wires. So keeping that in mind, but then the question is, please pay attention to this statement, a few long-range shortcuts. Why few? Because you are going to design the shortcuts using emerging technologies like photonics, wireless, 3D. These are costly. In a semiconductor process, your fab always go by established technology. Whenever you are introducing something, you are adding cost. So you always would like to utilize few long-range shortcuts. Then the question is, if it's only few, where to place them to achieve maximum performance gain? So this is the basic premise of the problem, that I cannot have, because if you have too many shortcuts, then again you are going back to that multi-hop fully connected system. Is few only limited shortcuts, and whenever something is limited, it's very important to understand where to place them so that I can fully utilize the capabilities of those shortcuts. So if you take a look at this plot, so basically beyond only when you're I'm giving the example with wireless, only when you cross a certain length, then only wireless is beneficial. Similarly for photonics, similarly for 3D. So then what we are going to do, see, you have only few of these shortcuts that you need to distribute. And this is the optimization challenge. Of course, wireless links are more efficient for long-range communication than at few long-range shortcuts. But then where to place them? Similarly for 3D. In 3D, what happens? Basically, you need to understand that in 3D, different planar dies are connected to vertical links, and these vertical links are only few microns. So what is happening? Though the processors or memory, they are in the different tier, different planar tier, but they are connected by very small vertical link. So again, the same concept. We say that they are physically far because they are in different planar layer, but they're logically near because these vertical links are small. But then again, the question is, how do I place them? How do I place the vertical routers? How do I place the links? So the utilization of emerging interconnects boils down to this question: how to place routers, cores, link? How do I map task? How to explore optimized link placement efficiently? So this boils down to an optimization problem. So let's go back, let's step back a bit and try to understand what we are doing. Basically, we are trying to place everything together and utilize the emerging links, interconnects in such a way so that we achieve significant performance and energy efficiency. So basically, in this optimization problem, you cannot do exhaustive search. So how to intelligently explore the design space to find optimal, software, small world network on chip. And here comes the role of the machine learning. As I said, what we do, we use machine learning to design efficient systems architecture. And towards the last part of my talk, I'm going to show that the different direction, how I can use hardware to solve efficient machine learning algorithms. So basically, we introduce the stage algorithms. So we run a base search and meta search to explore the design space suitably. So again, these are engineering details. We use regression learner and all these things. Again, we could have done something else. But this is the important thing. It's very important to understand. Take a look at, simulated annealing, genetic algorithm. These are well understood optimization algorithm, but stage converges much, much faster. Even after 1 hour of simulation, simulated annealing genetic algorithm, they haven't converged. And remember, this is one instance of the design. You will have multiple types of heterogeneous systems you may have to design. So you cannot just keep on wasting time. So something that converges in 6 minutes or 5 minutes, of course, that's better than something that even hasn't converged in 1 hour. So this is the beauty of machine learning algorithm, that I can come up with an optimized design faster than standard optimization algorithms. But how does it help? Why do I care for better optimization algorithms when we are talking about, complex heterogeneous systems? And here is the main thing, that when you have CPU, GPU, everything integrated on a single die, your CPUs, they are latency intensive. Latency is very important. And GPU, they are throughput sensitive. These are opposite trend. So here comes the role of multi-objective optimization. So if you take a look at this, you will, in one extreme, closer MC and CPU placement, so low CPU latency and the master core. And if MC, because remember what I said when I started my presentation, that a lot of GPUs, they're trying to communicate to the MC. But MCs are limited in number. So if you have, so see the counter examples. If you focus on CPU, because in your number of CPU is less than number of GPUs, because GPUs are the highly parallel architecture. So if you place memory controller and CPU nearby, then your latency is, CPU latency is minimum. But that doesn't help your GPU to memory controller communication. So to do that, you need to have well-distributed memory controller. And you can see some kind of unoptimized placements that either CPU and memory together, or CPU and memory at the two extremities. So why I'm providing you with this example, to make it clear that why a multi-objective optimization now becomes important. So basically, that's why how emerging interconnects like wireless, 3D, etc. On top of that, what is going, so the thing we are envisioning is that there are multiple planar layers and you stack them. So that's another level of complexity. So the point is that design complexity will increase in future architectures. So basically is complexity of the computing cores, complexity of placing them suitably, and the complexity of bringing new heterogeneous interconnects. So our search space is really huge, and it will be difficult to find good solutions. Let me give you a few. First, I'm going to provide a few examples, and then we'll show what's happening. So if in a 3D architecture, so we have multiple types of cores. They are placed in multiple tiers, connect through silicon via based vertical links. So this, of course, increases scalability. If we go 3D, it reduces network diameter, but then see what is happening. Basically, you are going to, in a 3D system, what is happening? You are squeezing your planar, your surface area is less, because you're going in the vertical direction. If your surface area is less, your power density is more. So basically, if you don't do anything, you can see you are creating congestion and you are going to create thermal hotspot. So this is example of where we designed a 3D system to speed up CNN training. We did good in performance compared to a 2D architecture using just a normal 3D mesh, but I created thermal hotspot. Remember, thermal is very, very important for high performance computing systems, cheap, wherever. You don't want to burn your system. So if I only 3D head part, please see the terminologies, that if I only consider performance, then see the right side of the figure, we have thermal hotspots all over. So then what do we do? Again, these are all motivational examples. We need multi-objective optimization now. So basically, first we talked about CPU latency, GPU throughput. Now I brought temperature in. There can be other constraints. There will be real-time constraints for other systems that you have to finish your computation within a certain time frame. So on and so forth. So that's why we need good multi-objective optimization. So to state the problem is that we have CPUs, GPUs, LLC tiles, certain number of planar link allowed. So we optimize the placement of CPU, GPU, memory controller tiles, planar links, because vertical links are given to you. So we have, suppose we have three objectives: GPU communication, CPU communication, and thermal. So keeping this in mind, basically, how do I GPU communication is network throughput. So to improve network throughput, I want to minimize the average link utilization and standard deviation so that there is not imbalance. CPU communication objective is that sensitive to latency, so I want to reduce the hop count. And then we have thermal objective. So again, see what the point I'm trying to make, that to increase throughput, I want the workload to be, the links to be load balanced. All the links and everything are being utilized equally. You are not starving anybody. But then to reduce CPU communication objective, you need to reduce the hop count. And then there is temperature. Remember, these are all kind of conflicting trades. So to give you an example, what we are trying to do, we are trying to, our objective means candidate solution space will be, our objective is to minimize your mean link utilization, standard deviation. You have hop count and thermal. But then you have to understand that the way we are going to design, you in a system, you should not have a single huge router. Because what's going to happen if your network, your system is not well distributed, if you create some hub-like architecture, if some attacker, and hardware security is a very, very hot problem nowadays, if an attacker attacks that router, it will take out your whole system. So always you have to, this is the Kmax, your number of link attached to a router, that is the router size, that has to follow a certain limit. You cannot have arbitrarily large routers. So keeping this in mind, see, we have a random starting network. We put the constraint that routers need to be of certain size. Then you bring up multi-objective MOO solver. So we can see only performance. Then we bring temperature, and then it is performance thermal joint optimization. And take a look. This is the most interesting part I wanted to show you guys. So in the left side design, you only focused on performance. So then you can see that GPUs are easily accessing memory controllers, all these things. In the right side, you have performance thermal joint optimization. See what happened. Though you left-hand design, you achieved high performance, you burned the system. Maybe you just ran for an hour and your system is gone. But see the right-hand system. You are never reaching that red temperature surface. So that's why in any high performance Manycore architecture, joint performance thermal optimization is extremely, extremely important. So if you take a look, your normalized hop count, of course, with respect to when it was mesh, compared to mesh, only performance, because what's the performance? Your CPU memory latency is minimum. So yes, you are the highest performance. When you did thermal optimization, you lost a bit of performance. But then, so that's why I'm saying 3D Hate reduces average inter-router hop count compared to mesh, but not compared to performance optimization. But only doing performance optimization doesn't work because you have burned the system. But, and see how good our links are utilized. When we 3D mesh only thermal, in a mesh, more than 10% of links have 2x higher link utilization than the mean, while some is 3x more. But traffic, if you take a look at the right-hand plot, is more evenly distributed in the heterogeneous architecture. So the point I'm making here is that if you are designing a CPU, GPU-based heterogeneous architecture, don't work with a mesh. Even if you do bunch of thermal optimization, mesh is going to fail you. That's why we should design application-specific heterogeneous architectures, but there also we should very carefully do multi-objective performance thermal optimization, because if I go to my previous slide, you will see if you don't do thermal optimization, you have burned the system on. 18 degrees centigrade lower improvement in temperature is lot in a chip. And you are, you have lost how much? If you take a look at this plot, very little performance. So in a mesh, even if after doing thermal optimization, you have traffic bottlenecks. In the heterogeneous architecture, application-specific heterogeneous architecture, you don't have that. So hopefully I have been able to convince the audience that we need efficient multi-objective optimization. But like the stage algorithm where we use only for performance optimization, we have to now work on multi-objective optimization. And then NSGA2, MOSA, these are well understood multi-objective optimization to find a Pareto set. But again, we worked on the ML inspired technique. So we actually modified the stage to call MOO-STAGE algorithm. And you can see that how the Pareto hypervolume changes in the right-hand side. So basically this, because Pareto hypervolume measures the solution quality. So again, we learn evaluation function to find better solution in less time. And see compared to MOSA, how much better is PHV. And again, I am converging very fast. If you take a look at this plot, your MOSA, the simulated annealing-based multi-objective optimization, it hasn't converged. Even after 95 hours, it didn't converge. So this is a real solid example that how machine learning-based optimization helps us achieving our goal. And now the question, you also have to understand this. So I talked about performance, thermal. within performance, I have to do load balancing for high throughput. Load balancing means I have to minimize the mean link utilization and standard deviation of link utilization. So if I continuously decompose my objectives, we have 2, 3, 4 objective different goals. And then a Rodinia benchmark suit is an application for heterogeneous architectures. So these are the different, you don't have to really remember what the applications are, but the most important thing is that as I increase my number of objectives, my performance gain of MOO-STAGE over AMOSA increases. Most important thing I highlighted in red, AMOSA never found the best solution like MOO-STAGE for 3 and 4 objectives. This is extremely important to understand that how efficient machine learning based optimization algorithms are. Because see, AMOSA is very, very well used and a very, very popular optimization algorithm. But when in this kind of heterogeneous system, when I have 4 objectives I need to optimize, see, it is never able to. It cannot find the optimum solution. But we are doing, again, if I go back to the previous slide, you will see the right hand side, AMOSA never converged. So I hope I have shown you guys that how machine learning can be used to design a better system. But then next thing I want to talk to you guys a bit, that how do I design better systems to solve machine learning algorithms? And there comes a concept called processing in memory. So though we use GPUs for machine learning applications, but remember, still data exchange is a problem. They're not optimized for machine learning applications only. So random ReRAM is random access memory, resistive random access memory. I have shown you the configuration in the left side. They are very, very efficient for matrix vector multiplications. Very high performance, very energy efficient. And see what is happening. The matrix multiplication itself is happening in the memory. That's why this is called processing in memory. And if you take a look at this, that ReRAM based design, they outperform GPUs for machine learning applications. Keeping this in mind, what I wanted to discuss with you guys. So basically, remember, now I am changing gear and I am talking about how I can design efficient architectures for machine learning. So what has been done in the community so far, that multiple these ReRAM based processing in memory cores, they are connected through a simple mesh, and they're very efficient, but there are limitations. First, they mostly do 16-bit fixed point implementation, so it's low precision, accuracy loss. They don't support normalization, and they are temperature dependence, thermal noise, because remember, it's a resistive device. In the audience, whoever you guys are EE student, they should be able to appreciate that resistive devices, they have inherent thermal noise. So then let's see what happens due to low precision and lack of normalization. In a CNN, you can see that in left side, all the gradients are very small. You cannot do anything. But with normalization support, I brought it to the right-hand side. So if we don't have normalization, gradients are too small. Low precision cannot represent too small or large values. Gradients will be rounded to 0. If all the gradients are rounded to 0, then there is no update. And if there's no update, means there is no training. Please try to understand, in a CNN, you need weight update for meaningful training. And if your gradients are too small without normalization, no weight update actually happens. Then thermal. Basically, as I said, resistance changes with temperature. Learn the terminology, resistive random access memory. So it works on the value of resistance. So resistance changes with temperature, it reduces noise margin, and you can see you're not going to decipher anything. Thermal noise can lead to all misrepresentation. And thermal noise increases with frequency. So what we do that's right, but remember, GPU is very good for this high precision computation, high precision normalization layer, etc. So what I have been talking about is 3D integration. Then what we decided, let's take help from 3D integration. I have multiple layers of ReRAM based accelerators, but I add one layer of GPU. So what happens? That GPUs will do the full precision part of the computation. And for low precision, we add something like stochastic rounding. If the number is low, then depending on a probability, I round it to 0 or some other number. And then for temperature, we added thermal reference cell. And we used something, I'll come to that, something called monolithic 3D to address temperature also. But the point I'm making here, see, what's the theme of my talk is heterogeneity. So this is another example of heterogeneous architecture to solve machine learning problem. Previously, what I was discussing about how we can use machine learning to build efficient heterogeneous architecture. Now I am talking about how heterogeneous architectures can solve machine learning algorithms efficiently. Now take a look at the accuracy. So GPU baseline, sole ReRAM, never match. Normalization, not much. But we do normalization for rounding, see the improvement. Then we get noise, again we fall back. We add, with the AccuReD architecture, see we are getting GPU level accuracy. So normalization, performance, thermal aware mapping, M3D, all these things together helps. So again, the point I'm making here is that you need to use a heterogeneous system, just don't use only processing ReRAM based processing in memory. And AccuReD, this architecture, you can take a look that compared to GPU, has GPU level accuracy, but up to 15x speed up. What can be better than that? So again, that you need heterogeneous architectures and use heterogeneous architecture suitably for your purpose. But I used the term monolithic 3D. What is that? So that is another enabler for heterogeneous architectures. When we are when we talk about 3D, and I mentioned, then there are multiple planar layers of logic, and then they are connected through vertical links. See what is happening, all the logic circuit, everything is planar. Only the vertical distance, you are getting rid of global wear. But your logic is still planar. In M3D, so basically what will happen, that in M3D, monolithic 3D, your MIV, monolithic intertier vias, they are so small, your logic itself is actually vertical. So think about this. Instead of only using planar, your vertical, that is nanometer range. So what is happening? The circuits are becoming smaller. So less area, power, better performance. But then logic blocks span multiple tiers. With through silicon via, your logic blocks did not span multiple, that's still planar. With monolithic 3D, it spans multiple tiers. So again, how to do optimum placement. So when we design a network on chip in this kind of monolithic 3D, your routers are spanning over multiple tiers. Again, yes, means conceptually it will be lower average hop count, shorter communication, etc., etc. But how do you place them? And if you take a look, when we do this again, so we remember we talked about multi-objective machine learning based multi-objective optimization, and here see your design now, but you should understand that your design space is huge now. Because previously in a TSV-based design, you at least knew that my logic and router, etc., everything is planar. I don't have too many options for them. Here, I have more options. So my design space is huge. But see, if my design space is huge, my optimization algorithm is doing better. So basically, as I mentioned, that more complex design, more complex objectives you are trying to achieve, machine learning based optimization is outperforming simulated and link based design more. So this is the real concept of ML for ML. I am trying to design a system for CNN training, and I am taking advantage of machine learning based algorithm to optimize, placement of the links and processor scores so that I achieve high performance and energy efficiency. So basically, you can see normalized execution time is significant faster than TSV-based design. And what's the meaning of faster? Lower critical path, that means higher clock frequency. So again, the most important thing is that how do I utilize my resource? Continuously, repeatedly in today's talk, I have been talking about that. One good thing about M3D is this temperature. Because remember, in M3D, what happens, things are very, very thin, very small. Everything is virtually near the sink. That's why our design is much cooler than through silicon via-based design too. So it's not only high performance and power efficiency, is also much better thermal profile. So then the last piece of thing what I wanted to talk about is using this monolithic 3D. Then we went ahead, and here the concept of processing in memory is different. In ReRAM, when I talked about matrix vector multiplication, then basically we are saying that the computation is being done in memory. That's why processing in memory. This is, though we say processing in memory, this is processing near memory. Because M3D is so thin layers, the distance between processing in memory is very, very small. And then what we have seen that when we had TSV, due to thermal constraint, I could not integrate more than one logic layer. Here, I can integrate multiple logic layers and take a look at. So 85 degrees centigrade temperature is, is pretty bad. You are reaching the limit. So take a look at the TSV-based design. You reach just 2 layers of logic, you're done. Here, I have already integrated 4, still I'm okay. So GHMC, this is our name of the design with, we solved the K-mark counting problem, and you can see that always I am faster. So M3D allows, easily I integrated up to 4 logic layers. And if I use very sophisticated cooling, then I could have integrated even more. So the point I am making here is that processing in memory is a concept where for machine learning workload, we are doing the computation in the memory. Using monolithic 3D, I can do processing near memory. Because as monolithic 3D, everything is tiny, my communication data exchange between processor and memory is very fast and it doesn't burn the chip. So when we are talking about heterogeneous system design, both the concepts we need to understand, processing in memory and processing near memory. So this is the big picture we envision. That is, this is your conventional data center now, huge locations, unique cooling and all these things. What I envision is called data center on chip. What will happen using 3D integrations, wireless communication on chip and all these things, everything will be smaller. So a part of the data center, we should be able to implement on a single 3D chip. And then few of them should create the whole data center. So this is the concept. This is the ultimate goal we are working towards. That why do I need massive level of integration? Of course, high performance from small form factor. That's the thing, high performance from small form factor. But then when you making things compact, then your power density is increasing. When your power density is increasing, then thermal becomes important. That's why you need to do joint optimization. But by doing all these things, so the point I'm trying to convey is that we have worked on these tools and algorithms and architectures to make this vision a reality. And not only my group, others are also working towards this target, that how I can reduce the physical space of a data center. And how I can integrate this kind of data center on chip, few of them. Of course, one won't be enough, but still that will reduce my space requirement. Please try to understand, we build data centers where there is abundance of water resource. So those are constraints. If I can design, if I can integrate more and more on a single chip using 3D integration, that helps. And that's the ultimate goal. So basically, in conclusion, we need to find optimal designs, because more codes, more code types, different types of interconnects. So that's why we need ML-based design automation techniques. But on the other hand, emerging interconnect-based heterogeneous Manycore, that also enables us to achieve higher performance, lower thermal for machine learning applications. That's why we call it a virtuous cycle of machine learning for machine learning. Why do we are all these things? What we are doing? Ultimately, our aim is to evolution towards a data center on chip. A chip will do the job of a data center. With this final message, I'll conclude. I'll thank all my collaborators, students. I'm not the only person. There's a big group of people who work with me and my PhD students. I thank the funding agencies and thank you for your attention.
Are there questions for Dr. Pande? Oh. Let me log off from.
I don't have a question, but this is Asafo. I want to say thank you very much, Partha, for wearing your professor hat today for an interesting talk. Just wanted to comment on that.
Okay, thank you, Asiva. Thank you. So if the audience doesn't have any question, then I'll stop sharing, okay? Thank you all.
Thank you.
Thank you.